Technically, gravity isn't actually part of conservation of energy, but the issue is, in order to do more advanced conservation of energy type problems, you do need to be able to calculate gravitational potential as well as gravitational forces. So as a result, here's a few problems for you to go over to make sure you understand that before we go over to a complete understanding of conservation of energy. So let's look at an example. Imagine that there's a 15-ton planet, and remember that 1 metric ton is 1,000 kilograms. And we'll say that 1.5 kilometers away, there's a satellite, and the satellite weighs half a ton, 500 kilograms. See if you can calculate what the force being exerted on this satellite is. And for a hint, I'll give you the gravitational constant is 6.67 times 10 to the negative 11th meters cubed kilograms inverse seconds to the negative second. So armed with this knowledge, see if you can remember the equation and plug this into solve. And you might need a calculator. Let's go over this together. Let's start by writing out the equation, because as I've said many times, that's always the first step. Gravitational force is mass 1, which we know, times mass 2, which we know, times the gravitational constant, g, which I just gave you, over radius squared. So let's see what we have. Mass 1, 15,000 kilograms. Pretty big mass, but not all that large as planets go, so we shouldn't expect a super large gravitational force. Mass 2, 500 kilograms. That's a decent sized satellite. It's really hard to get stuff into space, so you want satellites to be super light. And radius, 1.5 kilometers, which is the same thing as 1,500 meters. So we have all the numbers that we need. So let's plug and chug. 15,000 times 500 times g, which I'm not going to bother writing out. You can just input that in on your own, divided by radius squared, or 1,500 squared. So I just plug this into a calculator to make it a little bit easier, and it comes out as 2.22 times 10 to the negative 10th newtons. Now this is astronomically small, and what you'll notice is a planet that size would really just be a very, very small meteorite, and as a result wouldn't exert a significant force on the satellite. And that's a sign of how weak gravity is. It takes a planet the size of the Earth, many, many, many kilograms, in order to exert even a large enough force, and that's a force that we can overcome just by jumping. So even though gravity seems like this tremendously impressive force, and in a lot of ways it actually is, it's the force that holds the galaxies together. On the small scale, when you're looking at pieces of matter that you could expect to find and pick up and transport using a truck, you don't actually see that significant of a force. So now one last quick question before we go, and that is, find the gravitational potential between 2 points around a planet. The planet itself, we'll this time say has a mass of 1 million tons, and metric tons once again, and try to figure out the gravitational potential between the surface of the planet at 10 kilometers and all the way out to infinity. Now this might seem impossible at first, but one of the things you can assume here is that any number divided by infinity just equals 0. And remember that gravity is 6.67 times 10 to the negative 11th. So pause the video, take a little while to try to solve this, and then we'll go over it together. So this seems really daunting, but it's important to remember that the change in gravitational potential is the potential final minus the potential initial. So what's the equation for potential? That's mass times g over r, and it's negative. So let's see. Our final one at infinity is negative mass, which is something, times gravity, which is something, divided by infinity. And now you can see why I didn't care what the things on the top are, because two finite things divided by infinity just comes out to be 0. So now let's take a look at closer back by the planet. The surface of the planet's 10 kilometers, so we'll say r is 10,000 meters, and the planet weighs 1 million tons, or 1 billion 10 to the 9th kilograms. So now we can plug this into our equation and see what result we get. Our equation is negative mg over r. And plugging this in gives us 6.67 times 10 to the negative sixth. So now what does that mean? Sorry, negative. Well, since this is our initial value, we have 0 minus this value. Which actually ends up coming out positive, positive 6.67 times 10 to the negative sixth. And because this is positive, that means that as we travel outwards from the surface of the planet, out towards infinity, the energy that would be stored in some object increases. And the energy here is joules per kilogram. So that means if we move 1 kilogram out there, we get a fairly small value of 6.67 times 10 to the negative sixth. But if we move it a million kilograms out there, we'd end up with 6.67 joules. And that's actually the amount of energy that it would take to lift off there, assuming no air resistance or anything. And this is incredibly useful. It's incredibly important to understand the difference between the surface and infinity. Because a lot of times when you're calculating things like escape velocities, how fast does a rocket have to be going to escape the surface? This is exactly the things we'd be calculating. So I hope you understood that. If not, it's probably worth going back and taking another look, because the next set of problems is actually going to include a concept very similar to this.